Today we're talking about rational and irrational numbers and some of the properties that go with them. Quick reminder before we get too far into this that a rational number is a number that can be written as a fraction. This includes all integers, right? Positive and negative whole numbers, because you can put them over 1 to create a fraction. It includes all fractions, of course, since they're already in fraction form, and all decimals that end or repeat. Irrational numbers are numbers that cannot be written as a fraction, and the only numbers that are included in this category are never-ending, non-repeating decimals. Some good examples of irrational numbers are pi, square root of 2, and square root of 5. Those are some of the main ones that people use when they're looking at irrational numbers. We also need to define closed operations. Addition and multiplication are called closed operations for integers because the sum of any two integers is also an integer. In other words, if I add two whole numbers together, I get a whole number answer, right? So that means it's closed for addition over integers. Same thing works for multiplying integers together. If I multiply any two positive or negative whole numbers together, I'm going to get in return a positive or negative whole number, right? So anytime I use addition or multiplication on any two of the same type of number and get the same type of number in return, whether it be fractions, integers, decimals, whatever, that's called a closed operation. Now on to inverse operations. You already know several inverse operations like addition and subtraction, right? If I add 3 and subtract 3, I'm back to where I started. So addition and subtraction are inverse operations. They kind of undo each other. Same thing happens with multiplication and division, right? If I multiply by 3 and then divide by 3, I'm back to where I started. Now we're going to add to that list a new pair of inverse operations, and that would be roots and powers. With roots and powers, I'm going to show you how roots and powers undo each other just like addition and subtraction work. So for instance, we're going to start with the square root of 9 equals 3. We also know that 3 to the second power equals 9, right? 3 times 3 equals 9. I'm going to take this 3 to the second power and I'm going to put it where this 9 is in my first little equation because they mean the same thing. That means that the square root of 3 to the second power is equal to 3. Remember we talked in class about how the square root is the same as the second root. So a second root and a second power basically canceled each other out of the picture and left me with just the base of 3. Same thing happens with all kinds of roots and powers. A cubed root and a power of 3, right? A third root and a power of 3, they'll undo each other right out of the picture and leave me with the base of 2. A fourth root and a fourth power just leave me with that base of 5. And I can go on and on and on. Fifth root, fifth power, sixth root, sixth power. Even bigger roots and powers like a 150th root and a 150th power will still cancel each other out of the picture and leave me with just the base. Same thing works for rational exponents, since this is just a root and a power. Remember how the top number was the power and the bottom number was the root? Let's take a look at what that does. I can rewrite that as a root. Now, I'm going to undo each of these separately so that I can show you where I'm going with this. First of all, I want to get rid of this cubed root. What's the opposite of a third root? A third power, right? So if I take this whole thing to a third power, I'm going to get just the 2 to the 4th left over, right? Because the third root and the third power, they're gone. And how would I get rid of that 4th power? With a 4th root, of course. If I do both, if I get rid of both the root and the power, I'm left with just the base of 2. Well, what would it look like in a rational exponent with a third power and a 4th root? Wouldn't that be a 3/4 power? So let me show you what happens. If I have a 2 to the 4/3 power and I do its inverse power or reciprocal power, that's like undoing the root and the power, right? It leaves me with just the base of 2. I can also look at the properties of exponents, right? 1 base, 2 powers. I multiply those powers together and I would get 12 over 12. 12 over 12 is just 1. So I would get 2 to the 1st power, which is the same as 2. Keep that in mind, and I'll tell you why this is important to know. We're going to be asked to solve equations for x with roots and powers in them. So I need to be able to get x all by itself, just like I would with any other type of equation. So I'm going to show you 2 ways to do this. One with roots and powers, and one with rational exponents. Let's start with the roots and powers. I want to work from the outside in. It's just the easiest way to do this kind of problem. So I'm going to start with getting rid of this root. Remember, my ultimate goal is to get x by itself. That's what solve for x means. So to get rid of a 4th root, what would I do? The opposite or inverse would be a 4th power. Keep in mind, however, that what you do to one side of an equation, you have to do to the other side to keep it balanced. So I want to take both sides to a 4th power. On the left-hand side, that 4th power is going to cancel out this 4th root. And I'm going to be left with the x to the 3rd power. On the right-hand side, I would put 125 to the 4th power in my calculator and get this huge number that's over 244 million. That's okay because we have calculators. Now x isn't quite by itself yet. I need to get rid of that 3rd power. How do I get rid of a 3rd power? What's its inverse? A 3rd root. What I do to one side of the equation, I have to do to the other to keep it balanced. The 3rd root and 3rd power simply give me x, and the 3rd root or cubed root of this 244 million is 625. So x is equal to 625. If I put 625 where x is, I can double check it with my calculator and make sure that's equal to 125. The second way to do this is to change my roots and powers into a rational exponent. So the 4th root of x to the 3rd is the same as x to the 3/4 power. I can use its inverse power, or 4/3 power, to solve this equation. Remember to do that to both sides. Take both sides to the 4/3 power. On the left-hand side, the inverse powers simply cancel each other out, or go to 1 rather, and I'm left with just x. If I put 125 to the 4/3 power in my calculator, I get 625. Both methods give me the same answer. Which method you use will most likely be left up to you unless it specifically says otherwise in the directions. Another thing you're going to be asked to do is to decide if an expression is rational or irrational And you're going to do that by evaluating each part of the expression individually. So here I have an expression. I need to decide if it's rational or irrational. So I'm going to start with that square root of 100. That's what I mean by evaluating each part individually. I know that the square root of 100 is 10. Easy enough. We're already rational so far. Now I need to look at the other side, however. 8 to the second power, 8 times 8 is 64. I need to find the cubed root of that. When I put that in my calculator or look at my cube root chart, I see that that's equal to 4. In the middle, this says it's asking me to add those numbers together, and I get a total of 14. Is 14 rational or irrational? Since I can write that as a fraction by putting it over 1, that's a rational number. So this expression, I can say, is rational. I need to show why I know it's rational, but that's kind of the gist of it. Let's take a look at one more example. I have 4 plus the square root of 5. The square root of 5 is a big, long, never-ending, non-repeating decimal, and then it's asking me to add that to 4. If I add them together, I still get a big, long, never-ending, never-repeating decimal. So this expression, it says, is irrational. Make sure you look at both parts one piece at a time before you add them together so you can decide if it's rational or irrational after that. So that's about it for today. Make sure you're writing down all the examples and any questions that you have so you don't forget to ask them in class. I hope you have a great day, and I'll see you next time.